Hello, everybody, and welcome to our latest Hubble Hangout. This is a place where you can learn about and discuss some of the science and discoveries of the Hubble Space Telescope. And today we've got a really good topic today. We're going to be talking about the most important image ever taken, at least as far as in my opinion. We're going to be talking about the Ultra Deep Field again, and some enhancements and some ongoing evolution of the image as it has progressed over the years, and we are going to go and really delve deep into some of the latest wavelengths that have been added to the image as well. So before I get started with the introductions, let me say that you can interact with us, ask questions, leave comments on the Q&A app that we're broadcasting from on Google Plus and YouTube, as well as monitoring the Google Plus event page and the YouTube page as well. So, and there's also the Hubble hashtag, the Hubble Hangout hashtag on Twitter that I'm also following. So please say, give us your questions and comments, and we'll have some time toward the end of the discussion to get to a lot of them. So I hope you guys will help us get the discussion going toward the end of the broadcast here. So my name is Tony Darnell. I work at the Space Telescope Science Institute, and I have been led here in a very long and fortuitous and circuitous route, I guess, to the Institute by this very image, the Hubble Ultra Deep Field, and we'll talk about that just a little bit. With me also is Dr. Carol Christian. She's my colleague at Space Telescope Science Institute. She will be helping with the discussion, giving us great insights, and also a lot of history and background on the Ultra Deep Field. Also with me is Scott Lewis from Spacefan News and KnowTheCosmos.com. He's here to also provide his unique perspective with us. So today...
That's how you describe it. It's a unique perspective.
What? Yeah.
I definitely have a unique perspective, Tony.
I know. That's why you're here. So, so with me today is the couple of members of the team who released the Ultra Deep Field, the latest one image. With me is Dr. Harry Teplitz. He's a research scientist at Caltech. He's also the science lead for NASA's Infrared Archive. So welcome, guys, and also Roger Windhorst he's a professor at Arizona State University, also a member of the team that put the image that we're about to discuss out. So welcome, guys, and finally, Dr. Anton Kokemer. He's also at the Space Telescope Science Institute, and more than anybody that I know, I think he and Carol, maybe Carol too, have as much history with this particular image. He has been in many hangouts discussing this, and he's also a member of the Frontier Fields team, which is sort of a sister project of the Ultra Deep Fields, because we talked about this last week. Frontier Fields is going to try and take 6 more Ultra Deep Fields in different areas of the sky. So welcome, Anton. Okay, so let's start just a little bit with some with this particular image, and Roger, I'd like to start with you. What was the motivation for, well, first of all, why don't you describe what you've done to the Ultra Deep Field, and then we'll talk about some of the motivation for it.
Well, I should begin to say that Harry led the team, and Anton was the one who probably first saw this image when it came out of his beautiful Drizzle software. The thing that I added earlier this year is when I asked Harry to have a copy of it. See, Harry and I were initially on competing teams, but we decided about 2 years ago to work together, because this ultraviolet imaging of Hubble is so important that, you know, the only way to get it done is get all the people together and do it. And so there were already, let's see, 9 filters that reached about the depth of 30th magnitude, which is very roughly 3 fireflies as seen from the distance of the moon, but the moon not there for the moment. And then I added these other filters in with proper weighting, just for entertainment, for just see what it would look like. And to my great surprise, it you know, emphasizing the blue colors properly, it was just out of this world, and gave it back to Harry and Anton, and then Zolt LeVay from the Institute came in and he did his magic, and I guess the rest is history. But I just wanted to see what 841 orbits would look like. Well, for completely different reasons, actually. I was, you know, thinking about what it would do for the James Webb Space Telescope, and here you got it, all 592 hours with these gorgeous colors. And, all these galaxies that are actively star forming, they look blue as they should because they're producing all this ultraviolet light, and it's just gorgeous.
I agree. I couldn't agree more. So, so Harry, welcome back. I'm glad you're all. Let me unmute you. There you go. So I would have started with you, but you went away, and now I still.
Yeah, I don't know. Somehow it knew that you were going to come to me, and that's when it chose to disconnect.
So why don't you give us your take on why did you do what you did with the Ultra? What was the rationale for it?
Well, so you probably said the Hubble Ultra Deep Field is the best view of distant galaxies in one small region of the sky ever taken. It's an incredibly sensitive image of galaxies that are far away with nothing close by in the way to block our view. So it's a really good place to look. And Hubble has been studying it for more than a decade now, and had previously concentrated on optical and near-infrared parts of the spectrum. Optical meaning the part of the spectrum that the eye can see, infrared being longer wavelengths. But what was missing was looking at the things that are bluer than the eye can see, which is the light that's produced by the youngest, most massive, hottest stars that are produced in distant galaxies. So by adding this new wavelength regime, we are able to study distant galaxies that are actively forming stars, and in a particular time period. So if you think about ultraviolet light that's produced in distant galaxies by young stars, NASA has spent a lot of effort studying that in local galaxies using both Hubble and some other satellites like the Galaxy Evolution Explorer. And we've seen that light with Hubble in very distant galaxies in the Hubble Ultra Deep Field, because the expansion of the universe and the Doppler shift means that we observe that light at longer wavelengths, so that the visible and near-infrared pictures show us that light in the most distant galaxies. But in between, there was a gap from galaxies that were emitting light 5 to 10 billion years ago. If we wanted to see the ultraviolet light, we had to use the ultraviolet capability of Hubble that's only come online with the most recent surfacing mission. And so filling in that gap tells us a lot about the study of galaxy evolution in this very great field.
So in that wavelength regime, what were the general ages of the galaxies that were in there? Like, you said, the infrared shows the most distant galaxies, the ones right, furthest back. So what does the UV regime get us? What range of?
If you think about it metaphorically, if you think about studying galaxies as like studying people, when you use Hubble's infrared, you see things that are essentially baby galaxies. You see galaxies in the very distant universe within 1 billion years of their formation. And when you study galaxies in the ultraviolet locally, you're seeing grown-up galaxies. But in between 5 to 10 billion years ago, you had galaxies that were in the process of growing up, so sort of teenage galaxies. So they were a few billion years old at that time, but they weren't finished evolving into galaxies that like we see today.
Awesome. So Scott has a good slide up now that sort of answers the question, why was the UV important? And so as it says there, you can get an idea of sort of where in the wavelength range we're talking about. Also, I'm going to put up a quick graphic too that shows what instruments were used to make this observation. So here are all of the different detectors that are in the Hubble Space Telescope's image plane, and you can see that the Wide Field Camera 3 is right in the center. There's also the Advanced Camera for Surveys in there. You can see where NICMOS and STIS and COS, all of the different areas of the image plane where these detectors are. But off to the right, is it overlapping with C3, Carol? There's UVIS 1 and 2.
Right.
So
I could say a word or two about that.
Yes.
Go ahead.
Can I just, before Anton says something, so what you're looking at in that graphic is, imagine that you had a very large lens and you had a camera back on it. that's what we have. But our camera back has several different kinds of cameras on it. So it's as if you had several little cameras all stuck together and one big lens. So that's what you're looking at. You're looking at all of those cameras, and imagine that the telescope is coming straight out of the screen at you. And so the idea is the light comes into the mirror, it bounces back to what's called a secondary mirror, and then it comes down where all these cameras are. And all that light gets collected. So instead of being collected by just one camera like your home camera does, we have the ability to use all different kinds of cameras to look at different kinds of light. And Anton's going to explain about the Wide Field Camera 3, which was installed in 2009.
Okay, go ahead, Anton.
Okay, sure. So what you're looking at, as Carol said, is basically you've got these different cameras. Each one is like one of the cameras that you normally use at home. They, in fact, have about the same number of megapixels. These are basically 16 megapixel cameras for the UV that we're talking about today. Tony was asking why these are on top of each other. Basically, this instrument can let you look at either infrared light or UV light, just not at the same time. And so there's a little mirror inside there which switches between the two, or in fact it's a prism. So you can choose to look on the sky either in ultraviolet, which is what we're talking about today, or in infrared. In fact, a neat thing about the ultra deep field, so Tony was mentioning that it brought him into this field a while ago. It's actually 10 years this year that we've been looking at this field. 10 years ago is when we did the original ultra deep field release with the advanced camera for surveys. That's the camera that's slightly off center there.
Yep.
And that's deep optical, basically. That's things like red, green, and blue wavelengths. A few years ago, you might remember a hangout we did a year or two ago for the infrared ultra deep field, and that's also in the central part of the Wide Field Camera 3, but that's the infrared, and so that let us see all of the, basically the longer wavelength emission from galaxies. And so today we're going to the other extreme. Today we're going to the ultraviolet, and so we're really adding the final missing piece for this ultra deep field. Today really is the first time that we've got complete wavelength coverage across this field. It's taken us about 10 years to build up, and about 600 hours worth of exposure time, so it's a long time.
So, Carol, he brings up a good point. 10 years was when the first observations were taken in this area of sky, and even before that, there was another deep field. It was just called regular old deep field.
That was regular old deep field, right? Yes.
That was it. That was about 20 years ago, or no, that was 96, I think, right? They took that one. So, but that was in a different area of the sky, different instruments, and wasn't as deep as I understand that the ultra deep field was. So. One thing about astronomy that you can do with images and telescopes is that when you keep staring at the same part of the sky over and over and over again, and you can add all of that up, and they will stack up, and each one really does add to the other. That's one of the really cool things about astronomical imaging. In fact, what you don't want to do is open up your camera and stare at one part of the sky for, hours and hours, because the detector will have a lot of noise in it, and it's not as ideal. What you want are a whole bunch as short as possible exposures, and then when you add them up, the signal adds up linearly with each one that you add, but the noise only adds up as a square root of the number of those. And the reason I say that is that we take advantage of that in astronomy to make some images that we would not be able to see otherwise. Now there are limits to this, but and Frontier Fields has found a very clever way around the limitations of the Hubble by using gravitational lenses to boost signal. This is one way in which we've done it, and we've been looking at this area of the sky now for, as Anton said, 10 years. So would you guys say this is the most studied area of deep space?
Mm-hmm. For the purpose of this kind of study, that's true. There are other very interesting questions you can ask that are studying different things. So, this doesn't tell us anything about our galaxy. The great thing about this is our galaxy is not in the way.
Right. So we can see things. We can see, as you were pointing out, with the different wavelength ranges and the different distances with which we can see. We can also see galaxies in various parts of their evolution. Now, I'll put up this graphic of the ultra deep field where it is. This is the area of the sky. It's in the constellation near Fornax. It is a rather unremarkable area. I mean, when you look there with a telescope, you don't see much. But Carol, how big of a piece of the sky is this that we're talking about here?
Well, Anton probably knows the analogy, but it's a very, very small piece of the sky. Anton, you can probably tell me exactly how. Do you have an analogy? It's a good analogy.
The easiest way is when you look at the moon. This is about 1/10 the diameter of the moon. So some of those larger craters on the moon, maybe that are 10 times the width
like
of the moon, this would basically fit in one of those craters if you were to just look at it.
That's a good analogy.
Yeah,
so the point is that it's a very small part of the sky, and so a lot can be learned. And Harry actually talked about it a little bit, is that when he was describing the different kinds of nearby galaxies, the baby galaxies, and in between. And so we do tend to look at stuff nearby because we can see it, resolve it, look at it in detail. But we're always interested in looking at the baby galaxies because we want to know what happened in the beginning. But we have to link those together, like what was going on in the early universe that produced these beautiful spiral galaxies, these lovely elliptical galaxies, or these tiny little dwarf galaxies that we see today. So it's important to look at all different times to understand what was going on, how fast the stars were forming, where the gas and dust went. And so that's why the ultraviolet was important in this particular field, because we knew a lot about a few nearby galaxies, but mostly distant galaxies, and you want to bridge that timeline. You know, it's like your Facebook timeline. You only have the beginning and the end. You need the in-between. And so adding to the observations, and I will also say that in addition to HST, the thing about the deep fields is that other observatories are used to look at different aspects of these deep fields as well, which adds to our knowledge in general.
Yeah, I think that's a very good point, that the Chandra X-ray Observatory and the Spitzer Space Telescope that looks in the infrared and the Herschel Observatory have all looked their deepest images here too.
Right.
And what did Chandra see?
Chandra saw, well, Anton, you've been working on this, but a good number of active nuclei in the X-rays, right? Weak ones in particular.
So they would have seen a bunch of very bright X-ray sources that would have probably been the centers of those galaxies.
Exactly. So Chandra has, in fact, spent almost 10 million seconds of integration time on the field now. And so you've got this really great legacy field. Spitzer has also spent a lot of time. And when you look at the Chandra image...
Wait a minute, did you say 10 million seconds on this field?
Exactly, yeah. So 4 million in hand
5 times
already.
longer than Hubble, right?
I did not know that. I did not
It's been
know
extended, so it's busy accumulating as we speak. The initial 1 or 2 million seconds showed us, as Roger said, all the active galaxies. Basically, every time you have a black hole, you have gas. When you throw gas around a black hole, it heats up and it gives off X-rays. And you can see that with Chandra. And so the first couple of million seconds, every little optical galaxy you see with Hubble, if there's a black hole at the center of it is active, you'd see that in the X-ray. So the Chandra image, all the black holes light up, basically. As we go deeper with Chandra, you start seeing X-rays from other things. Our sun gives off X-rays. If you look at our sun in X-ray wavelengths, you see that. And so normal stars or certain types of stars can give off X-rays. Supernova remnants, when a star explodes, that gives off X-rays too. So as we go deeper with Chandra, we begin to see more and more X-rays, not just from the active galaxies with black holes, but actually from the normal galaxies. And so ultimately, in this ultra-deep field Hubble image, many of the galaxies that we would call normal are actually also showing up now in Chandra. They basically, we're going deep enough with Chandra to show very sensitive X-ray emission from the exploding stars and other things in these galaxies. So it's a very nice complementary data set. It's actually, I think, unique in astronomy that you go this deep with so many different wavelengths.
I have a question about that then. There's been many beautiful composite images of Chandra and Spitzer and Hubble. Have we been able to put together of all these different observatories into like the ultimate ultra deep field with all that data? I mean, that's 10 million seconds of observation. I think would really be great to help supplement to even give a more beautiful image coming out there. Has that been done?
It's a good idea. They have different resolutions. That's one thing that you notice first when you do that kind of comparison.
Right.
In fact, 10 years ago, I did an image like that when I found certain types of galaxies that you didn't see in the optical at all with Hubble. You only saw them in Chandra and Spitzer. But we looked at Hubble as well. And so when you make a composite image like that, you discover that the Hubble, the amount of detail you see with Hubble is so sharp compared to Chandra and also Spitzer that a detailed galaxy with Hubble comes up basically as a sort of a fuzzy blob maybe with Chandra or with Spitzer. So what you have is a detailed Hubble image with then fuzzy blobs from the X-ray and the IR from Spitzer. And so, yeah, you can do it, but they have very different resolutions.
Let me make let me make a comment on that too. What Anton said is right. You're seeing different things, different resolutions. Another thing to remember, from X-rays all the way to radio, where the Hubble Ultra Deep Field has been observed with Chandra and Spitzer and the Very Large Array and telescopes in Australia, it's almost 20 orders of magnitude of wavelength. It's sort of, sitting in front of your Comcast TV and flipping through all 10,000 channels. Only maybe 10 channels of which show the stellar population, and the rest shows other things, which are relevant but still different. And when you combine them, you'd have to really think hard before it makes sense. But
so the context of the different
observations, you see the stars from blue to red everywhere.
Okay, yeah, that makes sense.
I think it's important to remember that we're talking really about the exception, though, of pictures that combine Chandra, Spitzer, and Hubble. If you look at things that are close by, the original question is exactly right. You got really incredible images if you look at nearby galaxies. Just last week, Hubble and Chandra released a spectacular image of the Whirlpool galaxy. It does exactly what you say. It shows you the X-ray light and the optical light on the same scale, and it's really quite spectacular.
That's beautiful. Let me point out another thing, Tony, that's important for folks to realize. When you have a telescope like Hubble, and you go for 10 years, you spend a week a year or some number like that to look at that same field, and you go deeper and deeper and deeper. The deeper you go, it is not necessarily true that you actually look at earlier epochs, or what we call astronomers higher redshifts. You just begin to look at intrinsically fainter objects, and that's because of a conspiracy between the amount of volume that's available in the cosmos in the early days. At higher redshift, the universe is smaller, and therefore there is less volume you look at, so there's fewer galaxies. And most of the star formation happens when the universe was about half the current age. So with the current ultraviolet rendering, when you go deeper and deeper, you begin to pick up all these relatively faint, halfway through the edge of the universe galaxies that we see. I liken it a little bit to the cosmic stock market, if you wish. If you look at Wall Street, there is, IBMs and Microsofts, and then there is small cap companies. In the cosmic stock market, there is all these tiny galaxies that do most of the star forming power, and there's in fact very few of those giants. And so what we do at the Hubble Ultra Deep Field, you look deeper and deeper into these small cap companies, if you wish, that do the collective cosmic star formation. And I want people to realize that, and that's why the image looks blue as it should, because you see all this ultraviolet light from these galaxies that are not all that far away, maybe halfway between here and the Big Bang.
Yeah, let me put it up real quick. So I'm going to run this little animation here that we put out in the press release. So it starts by showing where in the sky we are. There's the constellations and the general area in which we're looking, and it sort of zooms way in, and we're getting past the stars in our galaxy and going ever deeper and looking at this little tiny patch of sky that Carol and Anton were telling us about, and here it is. So this is the image that was released, and as you can see, there's a lot of blue in there, an awful lot of a lot of galaxies, and 10,000 in this picture. Every single dot, smudge, and smear, with the exception of a few foreground stars, is an entire galaxy. And I don't care how many times I look at that, it's incredibly humbling, and I can't help but get emotional over it. This image, I'm not overstating it when I say this image has changed my life. I mean, it really, really has. And Anton's heard me say this before in all the hangouts we've done, because he always is in the hangouts where I'm doing this. But it's like it's just stunning. When I posted this on Twitter, it went crazy. Scott did a video on it, and it blew up. I mean, everybody loves this image, and so I don't know.
Okay, so I'm going to get back to the science. It's all good. I want to. Roger said something very interesting about the small galaxies having a big important role in star formation, star and cluster formation and production. I remember, and this is not my field of expertise, but it seemed to me, you know, being in a different field, subfield of astronomy, that when we first did the deep fields, and we did the Hubble Deep Field, that there was a lot of emphasis on merging, of understanding mergers and how galaxies came together and they built bigger and bigger galaxies, and then we saw those today. And over time, now it does seem like it's becoming more and more important to understand what the little galaxies are doing, because they, in fact, may be where a lot of the production is. And I think that's interesting in the history of deep fields, that sort of the emphasis on what we're thinking about as far as star formation and where stars and galaxies come from has changed a little bit because of these types of observations.
Yeah, indeed, Carol. The power of cosmic star formation is to the little galaxy guy in the street, so to speak, right? It is these tiny things that are doing it collectively. Yeah, they do merge, and they do grow bigger galaxies over time, like, you know, companies on Wall Street become eventually Microsofts and IBMs. But there's very few of those, even in the Hubble Ultra Deep Field. If you look at these big, giant red galaxies, the giant ellipticals, there's not too many of those, and those are the end products of the mergers. That happened actually a fairly long time ago.
Yeah, there's I think one of the largest galaxies in the universe, IC 1101's elliptical, and it came from just all these merging. In fact, when the Milky Way and the Andromeda Galaxy collide, they will form an elliptical galaxy too. So yeah, these are, you don't see too many of those. But we just did a press release today on dwarf galaxies, right, Carol, where there was they were talking about the rapid rate of star formation.
Yes, so it's a different observation, but yes,
it's a different observation, but
it was along this same theme, and it just seems to me, I'm seeing more and more science papers about this, is that these small galaxies, when they're studied in detail, is that they are having a more important role in the formation of stars, and then subsequently the formation of galaxies. So sometimes what we may be looking at, the galaxies we see today that are closer to us, may have come from several of these kinds of smaller galaxies that had very rapid energetic star formation. And so it becomes an interesting puzzle to try to forensically disentangle that. And there is sometimes is evidence that there was more than one object that formed the thing that we would see today.
And I think that the two results, that's an important thing that Hubble offers, right, is that Hubble has a couple of different ways to study these very small objects. The thing we're looking at in the picture that's on the screen now is the pointers we were making was the UV, the ultraviolet light. The press release today is actually about looking at it in the infrared, even though it's very similar sources.
Yes, yes. But the key point there was what Carol was mentioning about how these dwarf galaxies are probably responsible for the vast majority or a large proportion of the star birth that we see, or the stars that are in the universe. So
I think the way we phrased it today is it's more than their fair share.
More than So here we have the deep field. This is what we see when we stare at a patch of sky where nothing seems to be. What are your opinions on how ubiquitous this is? And Anton's working on Frontier Fields, which is a project that's designed to try help answer this question. But I wanted to open the discussion up to you guys. Is this common, do you think, or are we going to? Is it going to be very different if we look somewhere else?
This is common. One of the basic fundamental assumptions in astronomy that has been borne out through all kinds of tests is that there are no special directions in the universe. There are special directions in our galaxy, but we're not looking at our galaxy here. The universe is very similar overall on the largest scales. So if you can find something where you can look far away, it should look in a gross scale like this.
But when you see things like the cosmic web, those animations where there's these tendrils of galaxies on the large-scale structure of the universe, that sort of tells me that you could probably get to a spot where there isn't a whole lot of galaxies. It would be different.
But that web is this picture that we're looking at is very small when you compare it to the moon, but it goes very, very far. So if you think of a pencil, the web is a slice, or if you think of a tree, right? A tree is very tall and thin. If you slice a tree, you'll see rings, and maybe even those rings could be different at different spots along the tree. But the cosmic web is like a slice, whereas this picture goes all the way up the tree. So if you average out all the way along, the average is the same, even though in detail along the way there might be denser and less dense regions.
Right.
But if you look back 10 billion years...
Scott's got a picture of it there.
There's indeed a few clumps here and there, as Harry says, but the average is pretty average. And we looked at that a couple of years ago for adjacent fields in the greater Goods area, and compared to other even larger fields done from the ground, and we find that on average the count, the number of galaxies, is no more off than about 20–30% in the Hubble Ultra Deep Field compared to what you observe on average, which is pretty good. That's not to say that you can't find a redshift or cosmic epoch slice where there is bigger than average pileup.
I'd say a good word for this field is that it's representative. It basically shows you a typical slice of the universe. Now, when you look at it, you actually see the galaxies are not completely even across it, right? I mean, there are some spots where you have more galaxies and some where you have less. And basically, what you're looking at is you're looking through this cosmic web. You're sort of seeing superpositions of all the different clusters of galaxies on top of each other. But in general, it's a fairly uniform field once you average it out.
It's even more mind-boggling to think about that. I mean, you kind of hope that it would be a strange, special situation, but now you know you've got galaxies all over. So I always use the 100 billion rule. What do you guys think about that? There's about 100 billion galaxies in the universe, each with about 100 billion stars. Is that that's too simplistic? That's what I always tell people. We had a question like that on Twitter last week.
When you include all those dwarf galaxies, I would call it closer to a trillion.
A trillion?
You used to be able to say that there is about as many galaxies in the universe as dollars in the national debt. It's not quite true anymore. The number of galaxies is still roughly the same.
Yeah, that's depressing on a different
Praise
level.
the Lord.
Yeah, so the universe is going to have to go to war a little bit more to get it back up there.
And the number of stars in a giant galaxy, like these big red beasts in the image, is also about almost a trillion.
Okay.
And then, of course, the tinier galaxies have far fewer, maybe only 10 or 100 million stars.
Okay, so that's a gross simplification. Then it sounds like I have to start giving a different answer.
You want to state it differently. There is about as many stars in the universe in all these galaxies, if you multiply the trillion by the 100 billion, as there is atoms in what we call a mole, Avogadro's number. And that's a good number to keep in mind. About 10 with 23 zeros.
Wow.
Yeah.
Nice and
so I wanted to mention something else. I mean, there is the thing about, is this representative? We do have different kinds of data, like the cosmic microwave background, which suggests that when this all started, it was more or less uniform. So we do.
I mean, very uniform.
We have other expectations from other data that, if this was unique, then something really weird must have happened between that epoch and when the first galaxy formed. And we still don't totally understand that process. But if we're somehow cleverly picking out the special place in the universe to look at with Hubble Space Telescope, it's very unusual because other data suggests that that's not the case, in addition to the ground-based optical, infrared data, and X-ray data that people have collected.
That's true. Yeah, that's true. There's an awful lot of other representative data too. So, Roger,
I'm going to preempt you, Tony. Sorry.
Okay, go ahead.
I want to ask Roger about like dark matter and dark energy. What does looking at this, you know, you're mapping out where the galaxies came from, where the you know, middle-aged or the teenage galaxies are. Does that tell us anything about dark energy, dark matter, any of that stuff? Sorry, Tony.
No, that's a good question. I was going to get there eventually. Good.
Yeah, those are very good questions. Of course, only about 4% of what we know must exist in the universe is inside atoms and stars and matter that we can eventually see, although even all of that doesn't glow either. The other 96% is very roughly divided in a third dark matter and 2/3 dark energy, and those fact how much gravity there is for the dark matter in any specific region, and how much curvature of space there is as far as the dark energy is concerned, and how the expansion evolves as a function of time. And all of this you can measure somewhat with galaxies. There are actually better yardsticks to do this, as you well know, like the supernovae inside these galaxies, some of which have actually been found in this Hubble Ultra Deep Field. So as far as dark energy is concerned, images like this and also future images at even higher redshifts with the James Webb Space Telescope will really help us to nail down this dark energy. Having said that, dark energy is such a global phenomenon that you actually must measure it over a much larger scale, and so NASA is now designing future missions such as WFIRST to do just that.
That's right.
Yeah.
So you brought up JWST, and one of the reasons, one of your motivations for looking at this image, or for taking this particular deep field that you've just released, was so that you could learn or get an idea about what to expect with JWST. What did you learn in that respect?
Well, my main interest of looking at this image, other than, of course, the great science that Harry and company have pioneered with the ultraviolet, is to see if you would add all the images together, if you would eventually come to a limit where you can't go any deeper because the galaxies start overlapping. It's sort of a little bit, you can't see the forest for the trees anymore. And we're not quite there yet, but a little bit more of that will happen with the James Webb Space Telescope. Now, the James Webb is a 6.5-meter telescope, so it's more than 2.5 times bigger than Hubble, which means at the infrared wavelengths, the further infrared wavelengths, even redder than red, that it will operate, it will have the same resolution as Hubble, and at the bluer wavelengths, as blue as the eye can see almost, visual wavelengths, it will actually have better resolution than Hubble. But it's primarily designed as an infrared telescope that will be launched in the fall of 2018 to look even further into space, earlier epochs, what we say call larger redshifts, earlier cosmic times, where the universe was so small that the light has been stretched so far since it arrived from there to us, that we must use infrared wavelengths to actually see these objects. So if you ask where's the very first galaxies, those would not be seen in this image, not in very large numbers anyway. There's maybe 1 or 2 candidates, but we expect there to be hundreds or even more, but that will require the James Webb.
Yeah, that's true. There's a lot of anticipation for being able to see these very first galaxies right up. I mean, just the very first ones that have ever formed. JWST is expected to see. But you said something I'm a little confused about, and Scott and I were talking about this last night. I know that James Webb is primarily an infrared telescope, but you said it could go out to the blue wavelengths?
Well, it can go to visual, about 6,000 angstroms or 7.
Okay, but not quite the UV, right?
Not blue. I lazily called it blue. I really mean visual. So the unique part of Hubble is the ultraviolet, and the real blue, what we perceive as blue. What we perceive as orange, yellow, that James Webb can just do, and then anything longwards of that by about a factor of 100. So it typically runs from 6,000 angstroms, which is orange, into the mid-infrared, about 29.
Okay.
Yeah,
I think you can get a kind of quick visual of that if Scott can look at one of the last pages in the slides I sent. There's a red and a blue comparison where you see that this, again, Roger made 2 different versions of the picture. One that emphasizes what James Webb will see versus one that shows the full range of Hubble.
Oh, okay.
Right. Yeah, thanks, Harry. I was just about to show that. Yeah, please do show that.
Okay. All right. So yeah, Scott will be getting that up soon.
I have them on my screen, Tony. If you can show my screen.
Well, you'll have to do it. So the way you'll have to press the screen share button.
I think he's got it.
He's got it. He's got it there.
Okay.
Okay. So go ahead and describe what we're looking at. 841 orbits.
Yeah. So the red rendered, there's 2 versions. There's a red rendered image, which is not a whole lot different from what you've seen before, except I stretched the red a little harder. And that shows all the current Hubble data with this particular emphasis on anything longwards of the orange, which is pretty much what James Webb will see. And you can see the galaxies are very densely packed because they have lots of older stars in their outskirts, which cause all this, orangey, reddish glow of light. And then if you look at the blue rendering of the same data, but where now the ultraviolet blue was emphasized, as it should be for the most of cosmic time, the one that Harry Taplitz et al. Released 2 weeks ago, that image is the same data but completely different rendered and differently rendered, and that's what Hubble now has seen. And the contrast between the two, if you can toggle the back and forth, really will give you a sense of what James Webb will see compared to what Hubble has now done.
Yeah.
And so I think if you look at the image, and I think maybe we're still seeing pictures of us, not the image. I'm not sure.
No, we're.
In any event, the thing about the blue one is when you look at the blue picture, that's something Hubble can do. But after Hubble, that capability is not going to be accessible for a while.
Yeah.
So we're in a sort of last chance to see situation with the ultraviolet.
Yeah, so you can see there's a lot more stars in any given area on the right image than from the left, and so I have always said that the future of astronomy. I just sort of when I'm feeling glib, I'll go, the future of astronomy is in the infrared, and the reason I always say that is that's an area of the spectrum that we've only recently had good detectors for, things like these new infrared Mercad CCDs, things like that that are actually sensitive to these wavelengths without being too noisy. And so, but I wanted to ask you about the UV. The UV seems very underutilized, or at least it's not as much as infrared for reasons that I think most people can understand. But what kind of science is most, and I know you talked about looking at galaxy formation. Is there any other kind of science that UV astronomy or the UV wavelengths are pretty good at, are good for?
Another thing that Hubble does is it can take not only pictures in the UV, but it can study spectra of the light, meaning that breaking it down by wavelength. And with that, that's how we know about this cosmic web that you're talking about. That you talked about earlier,
right?
That by studying things that emit at only particular wavelengths or things that absorb only a particular wavelengths, we can understand a huge amount of the detailed physics of not only what are the stars doing, but what's in the way of the stars. So what is the gas doing, where the gas might absorb something and that gas is an outflow from the galaxy, or what is the dust doing, because where you don't see UV is often important because it means that there could be dust or gas in the way.
Okay, so I want to get. We're starting to run out of time, and I want to make sure we get to some of the questions that we're getting on Twitter. From Libby Doodle, at Libby Doodle, is asking, JWST will be 2.5 times bigger, greater than 2.5 times bigger than Hubble. It will look even further into space. Is there a limit to how far we can see? Who wants to take that one?
Sorry.
I think the simple answer to that is yes, there's a limit, because the universe, we know that the universe started 13 and some billion years ago, so that's as far back as you can see. And in fact, even though you might not be able to take a picture that far back with James Webb, the cosmic microwave background that we mentioned earlier is a picture of as far back as you can see. And that's something that's studied with, for example, the Planck mission that has recently taken what they call the best picture of the universe ever.
Yeah. I guess a lot of it is the answer to that question is wavelength dependent. Microwaves can see the further they give us the absolute limit to how far we can see, but other wavelengths give us different areas as far as distance from the Earth. She's also asking, have we ever?
In terms of cosmic time, Tony, it becomes a little easier. So the time after the Big Bang, it takes presumably a couple of 100 million years for the first stars to form. This means you're from the Earth's Hubble's perspective, you're now looking so far back in time that all the light from the first stars is redshifted to the mid-infrared, and that's why you need James Webb. And so the first few 100 million years is what Webb can do. Hubble really runs out of steam at around 450, 500 million years. And so the first few 100 million years before that is what you need a Webb for. And if stars formed even earlier than that, you'd have to think about something next. And at some point you get into the dark ages where there's nothing there, and then you have to start using radio telescopes, because the only gas that shines is hydrogen, which is well seen in the radio wavelengths.
Right, and I mean we've managed to cheat the system a little bit with frontier fields by getting some help from galaxy clusters between us and Hubble to kind of boost the signal a little bit. But you're right. I mean we're reaching definitely at the limit to where Hubble can see now.
Yeah. So to add to that, I mean, so basically it's not so much a question of losing galaxies because they're faint, but I mean you do lose them too. But the main issue is that the light shifts out of our observed band passes. And so the further back in time we look, the higher the redshift, let's say, so the galaxies look redder and redder. So yeah, I mean, Hubble can only see galaxies up to a certain distance back in time, effectively. And after that, they redshifted so much that they go to James Webb. And in the James Webb, you can also see only up to a certain limit. And the question at this point is, are we going to reach the limit of James Webb before we reach the very first stars that are formed? Or are those first stars formed so early that even James Webb isn't long enough wavelength to see them? Chances are it's probably the former. Probably the stars are forming at a time that James Webb can see them. But basically that's your limit. It's sort of not so much a question of how far you can look, but really how deep back in time you can see them.
Yeah, and the reason I'm glad we're talking about this now is that also addresses a tweet that I did not get to last week from Scott. He's at Chaos020. When he asked the question, what is the maximum zoom of the Space Telescope? And Anton gave a really concise answer right there. It's not so much, zooming in as it is how far back one can see in time for these different.
There's a good question to that. It's just like a standard megapixel camera that doesn't have any zoom on it. Basically, your zoom is how much you blow the images up by. Hubble has a really long focal length, so if you think of it in terms of a focal length zoom lens, it's longer than your typical telephoto lens. When we take these images, when we zoom in on them, usually we expand them in digital form. So each camera just has a fixed zoom. We can't actually change magnification or the zoom on the cameras themselves.
Yeah, I guess it depends on what you mean by zoom. I guess so. You're right. I mean, you can blow up image or just make it larger, and that's a form of zoom. So, so we have some comments here. Craig Landon is commenting. I don't have the ability to highlight these questions. This is from the Q&A app. It goes, so for the Hubble Super Ultra Mega Deep Field image, how much correction has to be done to allow for? We haven't gotten Ultra Mega yet. That's a good one. We need to do that. How much correction has been done to allow for distances across the image over the course of 10+ years?
That's a very good question. So some things do move. Now, galaxies are so far away that over 10 years, the galaxy will still be in the same spot in the sky. But as Roger and Harry mentioned earlier, we are looking through our galaxy. And this image does have a few stars in it that are from our galaxy, actually. They're foreground stars. Basically, anything with a little plus-shaped cross around it is one of the stars in our galaxy. And guess what? They move. Over the course of 10 years, they actually move by enough to upset things. So when I make these images, I made the first one in 2004, and so it's sort of come full circle for me. Every time I combine these, I have scripts that align the images based on whatever's in them. And in standard astronomy, you align based on the stars, because stars are nice and sharp, and you can get a good centroiding on them. Well, for the ultra deep field, that's not a good idea, because the stars move, and so they actually upset the alignment. So when I do my registration, when I combine new images, especially these new ultraviolet ones, with the original ones from 2004, I actually have to discard all the stars, because many of them move by so much that they throw the registration off. But the galaxies themselves, they do move a lot. Of course, the stars, I mean, we're orbiting in our Milky Way around the center. But they're so far away, these galaxies, that we don't see any of that movement in the time scale of the 10 years that we're looking at. And same for the galaxy's evolution, too. Ultimately, galaxies change how they look over the course of the universe. You see them merging and evolving. But 10 years is not enough time to see that either. And so to all intents and purposes, the galaxies in the ultra deep field today look the same as they did 10 years ago. But the stars
what we can see change variable phenomenon though in these images, and in fact Roger mentioned a supernova, so those are sometimes we pick those up in these deep fields.
That's right. Supernovae and variable AGN, the black holes in the center, they change in brightness, so you can see those.
Yeah.
Especially over 10 years. So.
There is indeed one or two star-looking like objects in the ultra deep field that are quasars at a redshift of 1.5 or so. And so those will not have moved. Of course, there's not enough of those for Anton to align his images with. So at some point you have to use galaxies to align the images because you know they didn't move.
And the quasars have a bit of a galaxy around them too. It's quite faint.
That's
and
right.
It's usually drowned out.
Yes.
Quasars have a bit of a galaxy around them too. I like the way you said that.
Well, they do. You have to look very hard to find it sometimes because the light from the quasar dominates over everything. And in fact, I'm working with Roger and a few other people on another program to do just that.
But you raise an interesting point because the resolution of HST, I mean, you can work very carefully to align, over 10 years to align those images, right, that were taken sometimes with different instruments. But when you go to other telescopes, you have to have some of those fiducial objects in the field so that you can make sure that when you see a weird X-ray, that you know in the Hubble image which object that is. So the alignment from not only from Hubble image to Hubble image, but also from different observatories to different observatories is really important.
Yeah, they got all kinds of a lot of things to consider when you're adding these up. So, okay, I got to read this tweet. This is from Libby Doodle again. Thank you, by the way, for tweeting. I'm glad that someone is tweeting us questions. She goes, "Whoa!" And this is so that we can feel old. Hubble's Ultra Deep Field image was taken in 2006. That's when I graduated from high school. So, thank you for that.
Well,
I love being the youngest person on the show.
We were just talking about this. We were talking about there are people like Libby who've lived in a world where there's always been the Hubble, and for us that's not been true, right?
We've got students coming and starting their PhD theses now who were born after Hubble was born.
Yeah, it's great.
Yeah.
It's kind of crazy to think about. I mean, I'm fairly young. I'm not young, but I remember when Hubble came online. I'm fairly young.
Yeah.
I'm relatively young. The redshifting.
Compared to what?
Youngish. You don't redshift. You're not redshifted as much as some of us, right?
Exactly. But
I'm not wearing red today.
I may never wear it again.
I agree.
What's your Z number? But
what's your point, Scott?
But what we're talking about is we're seeing new ways that Hubble is able to bring insight into what's going on. We have frontier fields now, but now we're able to add 10 years of data. Thinking about that, just 10 years of information to present what this tiny pocket of our observable universe is. That's wonderful. And then we're going to be able to add to it with James Webb, and we have all these other observatories. And we have now people that are born with these great space observatories already there. It's not a point where we've never had that. It's something that's there almost like the internet is. What's the next generation going to be able to find out with these things that they're already born with, these tools already in hand? I think this is a great reason why we need to keep going on, keep these science missions going on, because new generations have this inspiration already handed to them, and they can build newer things.
Exactly, Scott and the tweeter. We need to keep the future generation in mind, right? This last month in May, Hubble transpired its official 5-year certified life after the surfacing mission of May 2009. Now, we're lucky many of these parts actually work a lot longer than 5 years, and we could well get another 5 or 7 years out of it. But someday in the future, we will no longer have Hubble with us. This is a great time to remember that planning for the next big ultraviolet optical telescope after Hubble, that would be launched after James Webb, is something that really ought to start this decade. And the young generation needs to step up there.
That's an excellent point. And there's a lot of hope that there will be some overlap between after JWST launches and Hubble will still be up and active and taking data as well. So we'll have them both up at the same time. At least that's the hope. Quick comment from Rashawn Rubin. This is from the Q&A app. When will we see a 3D map of the universe in a hologram form? I feel as if we're limited if we view and perceive the universe in a 2D form. For example, from a computer screen or paper, and
well,
that's
our
a
first
good
step's
point.
going on with Gaia, so that's our
Yes.
first step in that direction, which is a billion-star survey, which has faced some issues, but have been overcoming those issues really well. And that's just happening now. I mean, I'd like to see if we're able to push that out further as far as galaxies go. Do we have any way of implementing that?
I think the Sloan Digital Sky Survey for relatively nearby galaxies did something like that.
Yeah.
When they started mapping out things in, as you said, the cosmic web, they have a lot of information about nearby galaxies over not the whole sky, but a large part of the sky, and I think they did some sort of fly-through.
They did.
For the ultra deep field, in fact, we did this as well. So for these galaxies in the ultra deep field, we know how far away most of them are. We've got spectroscopy, and you can, for the ones that don't have it, you can estimate it.
Can I share this with you? I have a rendering
yes.
here that does that for the Hubble Ultra Deep Field, where you
see if you can put the movie up, because it flies through, basically starting from the local galaxies in the ultra deep field, sort of the bright foreground ones, and it goes for a couple of minutes, and it's available on the same website that you can get the ultra deep field images from. And it goes after you fly through. You see, as you go further back in time, the galaxies change their shapes. They tend to look different. And when you get to the very end of this video, the galaxies at those early times look totally different from the normal ones. They don't look like spirals and ellipticals anymore. They're kind of blobby and sort of funny-looking galaxies.
Yeah, so I guess it could
nice
be said.
So take a look at it. It's basically like flying through the universe in 3D.
Yeah, it is nice, but so it is possible. It is embedded within the data. We know how far away these things are in 3 dimensions. It's entirely possible to build a complete hologram you can stand inside of and project this if you want to. These are fly-throughs on a 2D surface, but there's nothing to prevent you, at least from the data, to be able to make a hologram or project this and even stand inside the ultra deep field, or as Harry was saying, the Sloan Digital Sky Survey was a ground-based survey located in New Mexico that did an enormous swath of the sky and was able to show all these galaxies also in 3D. So we have the data to accurately represent the universe in 3 dimensions. It just depends on what technology you want to use to display that.
Well, I think here's a cool idea for Oppo. I think, why did you make like a 3D fly-through that even if you just display it on the computer screen,
I agree. And Carol should
glasses.
print out the universe too. She has a 3D printer, so we should get her to print out the universe for us.
Yeah, there is a subtlety.
Fly through it.
I was afraid of that. It's right behind me, the 3D printer.
Make a 3D fly-through. You can put on your 3D glasses, and then you can see
Harry,
it.
you said you had to go. I just want to take a moment and thank you very much for joining us today. This was an amazing image. Thank you for your work, and as always, it's inspired a lot of people. So I want to thank you for going, and
Absolutely.
You can drop out at any time you need to. I know you got to go. So
yeah, unfortunately, I had another commitment, but I wanted to say thank you for inviting me to the hangout.
It's great. Thanks, Harry.
So thank you very much. And in fact, we're more or less out of. I think we're about out of time anyway. But we'll start with one quick question from Daniel Nasato, also from the Q&A app. Will there be any plans to bring Hubble back to be put into a museum or science center, or is it destined to burn up in the atmosphere? Who wants to take that? That sounds like a Carol question. You don't want to?
Well,
I'd be happy to take it. But go ahead, Carol.
Go ahead,
Roger.
I mean, go ahead, Roger.
Well, Hubble is too big to leave in orbit, right? If you just leave it there, it will eventually come down because of solar activity in the upper atmosphere slowing it down, and then you have an uncontrolled re-entry where it might hit a city, and that's just a bad idea. And so NASA has, in fact, in the last servicing mission, put on a grapple hook so that the robotic mission can grab it in the future, sometime after 2025, and push it gently in the ocean.
Okay.
There is also an alternative idea that some people would like to actually push it out further. So we'll see. Probably it will be controlled reentry. Unfortunately,
It
probably
would be
will
nice
in the ocean.
if we could go back once more and put a new suite of instruments in and push it out further.
Yeah, that would be
That
awesome.
would be really nice.
John
I'll
Grunsfeld.
volunteer for that. I'll volunteer for the service mission. I'll go up there. I'll volunteer my time for it.
I'll go with you.
All right. All right, Carol and I, we're going up to Hubble.
Fair enough.
See you guys later.
Well, John Grunsfeld made your job a little bit easier by putting that little grab ring on the bottom of it, so there's something to grab onto at least.
We'll have our space carabiners and
Yeah.
get on.
But Roger's right, is that the mirror itself is a big object, and you don't want that. It is a liability. It is in the project plan. You know, when we put this stuff up there, we have to have a plan for how to quote unquote dispose of it. And the nominal plan is to bring it back, and then controlled reentry is what it's called.
Yeah. Okay, so I think that's it for this hangout. We're running out of time. I just want to respond real quick to Jason Carr, who is asking where can we find a link to that 3D video. It was made in 2009. It's on Hubble site. Frank Summers made it with a lot of help from a lot of other people, and I'll dig up the link. But if you go to hubblesite.org and you go to the press section and you do a search for Hubble Deep Field in 3D, it should come up. But I'll also post a link.
I'll put the links. I've already got it up here. I'll put links into YouTube and Google Plus right now.
Okay, there you go.
Thank you.
All right. Thank you, Scott. All right, folks. Well,
Okay.
that's it for this week, everybody. Thank you guys for watching.
Yeah.
I'd like to
Thanks very much.
Thanks.
It was great.
and Harry for joining, and Anton for joining us. Yep.
Sure.
And
You're welcome.
Whoop.
everybody's dropping out like flies.
There we go.
On behalf of Carol and Scott Lewis, I'm Tony Darnell. Thank you all for watching, and as always, keep looking up.
Bye.
Bye.
See you later.
I don't get to press the stop broadcast button.
If you think about it metaphorically, if you think about studying galaxies as like studying people, when you use Hubble's infrared, you see things that are essentially baby galaxies. You see galaxies in the very distant universe within 1 billion years of their formation. And when you study galaxies in the ultraviolet locally, you are seeing grown-up galaxies. But in between 5 to 10 billion years ago, you had galaxies that were in the process of growing up, so sort of teenage galaxies. So they were a few billion years old at that time, but they weren't finished evolving into galaxies that like we see today.
Awesome. So Scott has a good slide up now that sort of answers the question, why was the UV important? And so as it says there, you can get an idea of sort of where in the wavelength range we're talking about. Also, I'm going to put up a quick graphic too that shows what instruments were used to make this observation. So here are all of the different detectors that are in the Hubble Space Telescope's image plane, and you can see that the Wide Field Camera 3 is right in the center. There's also the Advanced Camera for Surveys in there. You can see where NICMOS and STIS and COS, all of the different areas of the image plane where these detectors are. But off to the right, is it overlapping with C3, Carol? There's UVIS 1 and 2.
Right.
So I could say a word or two about that.
Yes.
Go ahead.
Can I just, before Anton says something, so what you're looking at in that graphic is, imagine that you had a very large lens and you had a camera back on it. That's what we have. But our camera back has several different kinds of cameras on it. So
Hello everybody, and welcome to our latest Hubble Hangout. This is a place where you can learn about and discuss some of the science and discoveries of the Hubble Space Telescope. And today we've got a really good topic today. We're going to be talking about the most important image ever taken, at least as far as in my opinion. We're going to be talking about the Ultra Deep Field again, and some enhancements and some ongoing evolution of the image as it has progressed over the years. And we are going to go and really delve deep into some of the latest wavelengths that have been added to the image as well. So before I get started with the introductions, let me say that you can interact with us, ask questions, leave comments on the Q&A app that we're broadcasting from on Google Plus and YouTube, as well as monitoring the Google Plus event page and the YouTube page as well. So, and there's also the Hubble hashtag, the Hubble Hangout hashtag on Twitter that I'm also following. So please say, give us your questions and comments, and we'll have some time toward the end of the discussion to get to a lot of them. So I hope you guys will help us get the discussion going toward the end of the broadcast here. So my name is Tony Darnell. I work at the Space Telescope Science Institute, and I have been led here in a very long and fortuitous and circuitous route, I guess, to the Institute by this very image, the Hubble Ultra Deep Field, and we'll talk about that just a little bit. With me also is Dr. Carol Christian. She's my colleague at Space Telescope Science Institute. She will be helping with the discussion, giving us great insights, and also a lot of history and background on the Ultra Deep Field. Also with me is Scott Lewis from Spacefan News and KnowTheCosmos.com. He's here to also provide his unique perspective with us. So today...
That's how you describe it. It's a unique perspective.
Decade now, and had previously concentrated on optical and near-infrared parts of the spectrum. Optical meaning the light, the part of the spectrum that the eye can see. Infrared being longer wavelengths. But what was missing was looking at the things that are bluer than the eye can see, which is the light that's produced by the youngest, most massive, hottest stars that are produced in distant galaxies. So by adding this new wavelength regime, we are able to study distant galaxies that are actively forming stars, and in a special, in a particular time period. So if you think about ultraviolet light that's produced in distant galaxies by young stars, NASA has spent a lot of effort studying that in local galaxies using both Hubble and some other satellites like the Galaxy Evolution Explorer. And we've seen that light with Hubble in very distant galaxies in the Hubble Ultra Deep Field, because the expansion of the universe and the Doppler shift means that we observe that light at longer wavelengths, so that the visible and near-infrared pictures show us that light in the most distant galaxies. But in between, there was a gap from galaxies that were emitting light 5 to 10 billion years ago. If we wanted to see the ultraviolet light, we had to use the ultraviolet capability of Hubble that's only come online with the most recent surfacing mission. And so filling in that gap tells us a lot about the study of galaxy evolution in this very great field.
So in that wavelength regime, what were the general ages of the galaxies that were in there? Like, you know, you said, you know, the infrared shows the most distant galaxies, the ones right, furthest back. So what does the UV regime get us? What range of? Yeah.
I definitely have a unique perspective, Tony.
I know, that's why you're here. So. So with me today is the couple of members of the team who released the Ultra Deep Field, the latest one image. With me is Dr. Harry Teplitz. He's a research scientist at Caltech. He's also the science lead for NASA's Infrared Archive. So welcome, guys. And also Roger Windhorst, he's a professor at Arizona State University. Also a member of the team that put the image that we're about to discuss out. So welcome, guys. And finally, Dr. Anton Kokemer. He's also at the Space Telescope Science Institute. And more than anybody that I know, I think he and Carol, maybe Carol too, have as much history with this particular image. He has been in many hangouts discussing this. And he's also a member of the Frontier Fields team, which is sort of a sister project of the Ultra Deep Fields, because we talked about this last week. Frontier Fields is going to try and take 6 more Ultra Deep Fields in different areas of the sky. So welcome, Anton. Okay, so let's start just a little bit with some with this particular image. And Roger, I'd like to start with you. What was the motivation for? Well, first of all, why don't you describe what you've done to the Ultra Deep Field, and then we'll talk about some of the motivation for it.
Well, I should begin to say that Harry led the team, and Anton was the one who probably first saw this image when it came out of his beautiful Drizzle software. The thing that I added earlier this year is when I asked Harry to have a copy of it. See, Harry and I were initially on competing teams, but we decided about 2 years ago to work together because this ultraviolet imaging of Hubble is so important that the only way to get it done is get all the people together and do it. And so there were already, let's see, 9 filters that reached about the depth of 30th magnitude, which is very roughly 3 fireflies as seen from the distance of the moon, but the moon not there for the moment. And then I added these other filters in with proper weighting just for entertainment, for just see what it would look like. And to my great surprise, emphasizing the blue colors properly, it was just out of this world, and gave it back to Harry and Anton, and then Zolt LeVay from the Institute came in and he did his magic, and I guess the rest is history. But I just wanted to see what 841 orbits would look like, for completely different reasons. Actually, I was thinking about what it would do for the James Webb Space Telescope, and here you got it, all 592 hours with these gorgeous colors and all these galaxies that are actively star forming. They look blue as they should because they're producing all this ultraviolet light, and it's just gorgeous.
I agree. I couldn't agree more. So, so Harry, welcome back. I'm glad you're all. Let me unmute you. There you go. So I would have started with you, but you went away, and now I still.
Yeah, I don't know. Somehow it knew that you were going to come to me, and that's when it chose to disconnect.
So why don't you give us your take on why did you do what you did with the Ultra? What was the rationale for it?
Well, so you probably said the Hubble Ultra Deep Field is the best view of distant galaxies in one small region of the sky ever taken. It's an incredibly sensitive image of galaxies that are far away with nothing close by in the way to block our view. So it's a really good place to look. And Hubble has been studying it for more than a